Proportions are everywhere. We use them constantly to compare quantities, whether we are mixing the perfect color of paint, figuring out how to share resources fairly, or calculating how fast we need to travel to arrive on time. They also govern the shakes around us. Take a standard triangle with interior angles of 30, 60, and 90 degrees. If we simplify that, the ratio of its interior angles is 1 to 2 to 3. Assume side lengths follow that 1 to 2, 3 pattern. They don't. Here, sides measure 1, 2, and the square root of 3. A 45, 45, 90 simplifies to a 1 to 1 to 2 ratio, but sides are 1, 1, and root 2. You cannot guess a shape's dimensions simply by looking at its angles. The physical side lengths of triangles follow distinct proportional rules. One of the most famous rules for those side lengths is Pythagoras' theorem, a squared plus b squared equals c squared. For a right triangle with sides of 3, 4, and 5, squaring the sides gives us 9 plus 16, which perfectly equals the hypotenuse squared, 25. We also use fixed proportions to connect the interior angles directly to those side lengths. These are our trigonometric ratios. Sine compares the opposite side to the hypotenuse, cosine compares adjacent to hypotenuse, and tangent compares opposite to adjacent. Let's look at how proportions handle mixtures. Imagine a painter mixing yellow and blue paint at a 3 to 1 ratio. If they use 12 liters of yellow paint, we know that those 3 yellow parts equal 12 liters. That means a single part equals exactly 4 liters. Let's test this with a custom purple paint. The recipe requires a 2 to 1 to 1 ratio of red, blue, and white. If we need 20 total liters of paint, try calculating the liters for each color. The ratio gives us 4 parts in total. Dividing the 20 liters by those 4 parts means each single part is 5 liters. So we need 10 liters of red, 5 of blue, and 5 of white. The critical step in solving any mixture problem is identifying what your starting number actually represents. You have to determine whether a value is a single share of the ratio or the total sum of the parts. Proportions also help us track how dynamic rates, like speed, change over time. This is a distance time graph. The vertical axis tracks the distance an object travels, and the horizontal axis tracks the time it takes. To find the object's speed, we look at the gradient, or the steepness, of the line. A steeper slope indicates that more distance is covered in less time, meaning a higher speed. A gentler slope means a lower speed. A common mistake is to see a flat horizontal line and assume the object is traveling along a flat road. In reality, a flat line means time is passing, but the distance is not changing at all. The object is completely stationary. Mathematically, the gradient is the change in distance divided by the change in time. If a car travels 120 kilometers in 2 hours, dividing that distance by the time gives us a gradient, and an average speed of 60 kilometers per hour. Always check for mismatched units. If a runner covers 8 kilometers in 40 minutes, you cannot simply divide 8 by 40. You must convert those 40 minutes into hours first, which is 40 over 60. Dividing 8 kilometers by that fraction gives us 12 kilometers per hour, which then converts down to roughly 3.33 meters per second. The physical slope of the line on a travel graph is a direct visual translation of the mathematical rate of speed. Whether dealing with geometry or motion, the proportional math is identical. We rely on fixed ratios and trigonometry to understand static shapes. On a distance time graph, the gradient equals speed, giving us an immediate visual read on fast movement, slow movement, and complete stops. Drivers, cyclists, and city planners use this exact type of proportional data to calculate arrival times, route traffic, and measure efficiency. Try sketching a distance time graph of your own commute to school. Think about where your line would sit perfectly flat while waiting at a crosswalk, and where the gradient would be steepest as you hurry to class. Mastering proportional reasoning gives you the tools to decode the mathematical relationships hidden in the shapes, mixtures, and movements we encounter every single day.